Someone asked about the law of cosines. So here's a refresher just in case you don't remember it from high school or it wasn't explained thoroughly or well or just a long time ago, any of the above. So law of cosines comes from, motivated by a theorem that everyone knows, which is the Pythagorean theorem. So if you have a right angle triangle with side lengths A, B, and C, then everyone knows that a squared plus b squared equals c squared. What that means is if you know what these two numbers are, how long those legs are, then you know what the hypotenuse is. Or you can rearrange this equation so that, let's say, if you know c and b, you could also solve for a. The problem with this is, what if not every triangle is a right angle triangle? What if you have this triangle with some angle? This is not 90 degrees. Pythagorean theorem, you must have this angle be 90 degrees. So what if you know these side lengths? You do know this angle, it's just not 90. Then could you find the length C? And the answer is yes. You need to know trigonometry. So what you do is you drop a perpendicular, meaning you start from this point, extend this line if you need to. If it's not an obtuse triangle, you won't need to. And then draw a line going through this point that's perpendicular to this line here. Now we've created a right angle triangle, so we have some hope of using the thing that we know, because we know that about right angle triangles. That's theta, so this angle is going to be 180 degrees minus theta, and that's very important. If you look on your unit circle, with an angle theta, this point is cosine theta sine theta. With an angle of 180 minus theta over here, you can see visually that this point is going to have the same y-coordinate, and the x-coordinate is going to have the same magnitude but opposite direction. So like this point is negative cos theta sine theta, even though that angle is 180 minus theta. So what we know then is that cosine of 180 minus theta is negative cosine theta, because this point is also cosine 180 minus theta, comma sine 180 minus theta. So similarly, sine of 180 minus theta is equal to sine theta. Those things have to be the same, and those things have to be the same, because they're the same. They're different names for the same point, so they must be equal. Okay, so that's very important, because then in this right angle triangle, you can use a number of ways to solve this, but you should be able to figure out, sorry about that, let me draw that line back in, maybe, if my stylus is working. You should be able to figure out that this bottom length of that right angle triangle is b cosine 180 degrees minus theta, which we said was equal to negative b cosine theta. How can that length be negative? Well, it's not. Cosine theta, because theta is obtuse here, is a negative number. So negative b cosine theta is actually a positive number. If I were doing this, with an acute triangle, hold on a second, my stylus isn't working, oh, here we go. Okay, if I were doing this with an acute triangle, where this was theta, this would be A, this would be B, then this length here would just be b cosine theta. But then what we would be trying to do is we would be trying to use this triangle, because our C would be here. So then this length would be A minus b cosine theta. Whereas here, if we have an obtuse triangle, that length is A plus negative b cosine theta, which in this case is positive. But you see how they work out to the same expression. That's also A minus b cosine theta. The signs, in this case, that number is negative, so we're adding something to A. But it doesn't matter. The math works itself out. So you don't have to necessarily draw the right picture, which is kind of cool. Okay, so that is that length. We also need to do this vertical length. By the same reasoning, this is b sine 180 minus theta. And remember, we said this other thing. So sine 180 minus theta, by those yellow things being equal, is equal to sine theta. So that vertical length is b sine theta. And that's going to be the same thing over here. This vertical length will be b sine theta. So in either case, we can use the Pythagorean theorem on that right angle triangle. So c squared equals the bottom length squared. In either case, it is a minus b cosine theta. And then the vertical length squared, in both cases, it's b sine theta. So we'll square both of those. We can expand this by the binomial theorem, or if you don't know how to expand it in one step, you can write out two parentheses and distribute. But I highly recommend at this level of math that you know how to expand this in one step. So that gets expanded to that thing. It's the first thing squared, minus, because this is a minus sign, 2 times the product of the two things, plus the second thing squared. Plus, and then this squared will be b squared sine squared theta. Okay, now we notice over here there's a common factor of b squared, which is not necessarily exciting because it's not common to the first two terms, but in this case it's exciting because of what it leaves behind. So if we factor out a b squared, we're left with cosine squared theta plus sine squared theta. But we know from trig and from that point being on the unit circle that cosine squared theta plus sine squared theta is 1. So that's great. So then c squared is a squared, and usually this term is written next, so plus b squared times 1, so just b squared, minus 2ab cosine theta. And that was the proof that the law of cosines is true, but now what you can do is you can walk up to any triangle with this angle theta, which is not necessarily 90 degrees, and if you know those lengths a and b and what that angle is, you can solve for c. This is also a demonstration of the side angle side congruence. So that says, just a quick reminder about congruent triangles. If you have two triangles and all three sides and all three angles are the same, you know for sure they're congruent, right? Everything about them that you could possibly measure is the same. But you don't need that much information, and there's a bunch of congruences. One says if all three sides are the same, then the triangles must be the same. So if you know the sides, then you can figure out the angles. This one says if we have a side, an angle, and a side in that order, so you walk around, you can walk in either direction, but you have to see them in order. You can't skip any sides or angles. The side, angle, and sides are the same, then everything else must be the same. But if everything else must be the same, I should be able to figure out what everything else is. And with law of cosines, I can use this side, angle, side. If I know those three things, I should be able to figure out that thing. And then with law of sines, that's this one. So let me just write that one down too. If I know A, B, C, because if you're rusty on law of cosines, you might be rusty on law of sines, little c. Then that says little a. Little a is the side length, big A is the angle, over sine of angle A, equals little b over sine of angle B, equals side length C over sine of angle C. And usually you'll only use two of these, but all of those are in the same ratio. So that can help you solve those triangles too, with side, angle, side, angle, side, angle. With side, 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 you've got to use law of cosines. So you can rearrange this equation. Sometimes you know what A, B, and C are, and you don't know the angle. So you can isolate cosine theta, figure out what that expression is, take the cosine inverse of both sides to get the angle. So law of cosines kind of validates. You don't need it to prove that these are true, but it validates that those work, and you can, in fact, figure out everything about the triangle. In this class, what it'll be useful for is sometimes with vectors, they'll end up forming a triangle. It's not the most useful thing, but it does come up, and because it's part of high school math, we do expect you to know it. So hopefully that was a good refresher, and hopefully you are able to solve problems where the law of cosines comes up now.